Thank you very much, Zvi, and great thanks also to the organizers for this very interesting workshop and for giving the opportunity to present. So this is a work that I have done with my student Felix Telander, who recently graduated from DESY in Hamburg and is now in Oxford, as well with mathematician Martin Helmer. So I was very fortunate to have Andrew give a talk before me this week. So probably you have already seen what Landau singularities are. And here is the outline of my talk. This will be essential notion, essential concept in what I will talk about. And yes, I will present precisely a new way to obtain it from what Whitney stratifications is. So after some introduction and summary, I will introduce the main notations I will use. And here is the meat. Here is where I explain to you what Whitney stratifications are and how one can obtain Landau singularities from them. Continue with certain examples of Feynman integrals we computed this way, and then finally conclude. So just to save time, I wrote down a little bit of the introduction and motivation. The topic, as we discussed, are kinematic singularities of Feynman integrals or Feynman-like integrals. These, of course, are objects that are at the core of calculations of theoretical predictions, both for collider and gravitational wave physics. In particular, yes, they correspond to, as we saw earlier this week, on values of the parameters of the integrals, in our case kinematic parameters, masses, momenta, where the integral becomes singular. And these kinematic singularities, or Landau singularities, they provide key information for actually getting values out of these integrals, of computing them, either analytically, which is perhaps closer to my heart, as these constrain or even predict, in many cases, as we showed in an earlier collaboration also with Christoph Dlapa, the symbol alphabets. These are core ingredients of the method of canonical differential equations, of differential equations in Hen canonical form. So knowing them in advance can really drastically simplify the calculation by rendering it into completely numerical one from still exact, but numerical from symbolic. Of course, these building blocks also allow one to circumvent even integrals in many cases and enable bootstrap methods, alternative bootstrap methods. And there are also asymptotic expansions, since still analytic, but also asymptotic expansions around the limit. So an expansion around the limit where some kinematic parameter takes some particular value. And then Einan and collaborators have shown that, Landau equations, they continue, yes, it's an active line of research. It's useful to find all regions, how to properly expand and include all terms in this expansion. And also same or similar logic is also used in numerical evaluation programs for Feynman integrals, like sector decompositions. Roughly, these symbol alphabets are integrable singularities, and so you need to somehow take good care of them so that they don't screw up the precision of your numerics. So all these are some. I guess it's not a complete list of where Landau singularities play an important role. So let me start by asking the question, okay, how do I actually compute this? These kinematic or Landau singularities. And there has been a flurry of activity in terms of, theoretical constructions, but also practical programs one could use. And there is, for example, the hyperint program of Eric Panzer, based on his work and also earlier work by Francis Brown. More recently, there is also the PLD, or Principal Landau Discriminants package, Julia package, again coming with certain important theoretical developments. But what I wish to point out, many of you may know this already. So it is well understood by now and admitted by everyone that this misses singularities. It does not give you the full thing. And especially, let's say, for these kinds of applications, you do need, it's a necessary ingredient to have at least an overcomplete basis, yes? That's not correct. This is admitted in the paper. It's not, a secret. They say they give particular examples. Even in the longer paper, it's 2 papers. In the second paper, they give particular examples where this fails. And I will come back to those examples also later on. More questions? So, and something perhaps that is also not well appreciated, this hyperint, it provides spurious candidates. I will not go into the detail, but this like Brown's construction simplifies the question of the task of finding singularities, but it gets something bigger, and then you need to work hard if you want to eliminate some of these spurious candidates. So with this, I can then summarize what this work is about. So. First of all, hyperint, so finding the Landau singularities is separate from the actual evaluation of the integral, and it can be done also in cases that are beyond usual polylogarithmic. This is the CG reduce command, but it relies on approximating, yes, so it relies on some approximation. So again, the integration algorithm is separate, and in order to get a final result, okay, in the end, if some integral is amenable to the integration algorithm, then you will get the exact answer, or at least in the epsilon expansion. This is it is used in hyperint mostly to know where the integral is defined. So where it is where one can safely evaluate it, so to speak. That's how it is used. And so with this respect, I guess it's also sufficient the way, yes, it is used in hyperint. Over-constrained, but if you want to use it, I don't know, this like subspace of kinematics where you know the integral is finite, it's still good enough if you want to get some numerical value, say, a fixed or constant or something of this sort. So with this, yes, the the punchline, and we will hopefully have time to go through this in detail. So I will present an algorithm that gives you the complete and non-redundant set of Landau singularities. And this I will do indeed based on some algebraic geometry machinery, that of Whitney stratifications. Oops. And the benefit here is that these have been implemented already in a namesake package, so in a Macaulay 2 package. So you can use them right away for the sake of computing Landau singularities. And then finally, as a bonus, we will see that in this process, we also get the singularities in kinematic limits. Of the original integral. For example, where some mass or p square of an integral goes to 0. So that's where we are heading at. And this is a good moment to pause and ask if there are any questions. Okay, then let's start to introduce the main players. And we will start from the so-called Lipomeranski representation of Feynman integrals. So if you have, so for integral with n edges and L loops, this looks like this. So this is an integral over the positive reals and xi are the integration variables. There are some gamma factors. And then there is the so-called Lie-Pomeranski polynomial raised to some power. And in particular, the Lie-Pomeranski polynomial is u plus f, where this is the so-called first, and this is the second Szymanczyk polynomials. And these are of degree L and L plus 1 in the integration variables. And this, the coefficients are constant or kinematic dependent. For each of the two polynomials. So these are standard objects of quantum field theory. I will not And they can be very easily derived from graph theoretic means by deleting some edges of the Feynman integral in the graph that you are talking about. So I will not present the exact definitions, but hopefully everyone is familiar with those, and you are welcome to also ask questions if not. U is the first semantic, F is the new. Oh, well, I'm going to that now. So we are in D equals 4 minus 2 epsilon dimensions. So this is, we are working dimensional regularization. The nu I are the generalized propagator powers. No, just dimensional regularization. This is something that is done in the physics community because it turns out that integrals that have the same ingredients but different integer values of nu's are linearly dependent. They have linear relations among them. Yes, if you took this to be arbitrary, you would also analytically regularize, but we assume that these are in the end integer values. Thanks for the question. Sorry? Double edges, yes, yes, triple and so on. Indeed, indeed. Yes. Yes? Could be, yes, I think you are right. Yes. And so I told you that indeed, exactly, this depends on, yes, some kinematic parameters. For each edge, you get a mass, and for each external leg, you get a p square, a momentum square. So this is where we start from, and then what we do is we, in fact, so this is a very well studied representation of Feynman integrals, maybe not the first one that comes to mind, but certainly, yes, it has received a lot of attention the past years. And it can be reached, let's say, from the more usual Feynman parameters with a different transformation, a dummy variable transformation. And then what we will do, we will projectivize it. And for this is similarly to how it's done in the more usual that I mentioned, Feynman parametrization. And so this, you will have to believe me, and I'm sorry that I invoke faith so early on in the talk, but roughly speaking, what you do is that you insert a 1, a particular version of 1, in the denominator, and then you do certain manipulations. And here what I can say is that these are very well explained also for at least for the Feynman parametrization, but it's similar what we do here, and also in Eric Panzer's thesis. Okay, so after some manipulation, the same integral, where I have dropped, let's say, the gamma functions and some other factors, this is now an integral over the positive projective space. So I have, again, okay, the integration, I have increased the number of integration variables. This is H, yes, d over 2. And now I have this additional omega. All right, what is this GH? GH is the homogenized Lipomeransky polynomial. So I just added an extra x0 here, and I turned this into a homogeneous polynomial. Previously it wasn't. And then I need to say what the other objects are. So you have that this omega is a n-1 form. N-I dx0 over x0 wedge dot 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 dxi over xi dot 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 dxn over xn, where this means omitted. So this means so each term in the sum has n-1 terms. Sorry, n terms. And then there is an additional nu 0 because I introduced this extra parameter. It's related, it's closely related to the superficial degree of divergence. Yes, and finally, this P n is, as I mentioned, the positive real projective space. So you have x0, x1, xn that are real. So in real projective space, and they also have that they are positive. So meaning, okay, you can think of this as the n+1 dimensional real, space of reals, where you remove the 0, then you remove the origin, and then you take all these variables and rescale them. Yes. The whole, yes, the whole thing is the volume form. Yes, this is the volume form, yes.
You could also get to there just replacing xi by xi over x0 everywhere.
I presume that would also be sufficient. But yes, so this is something that one could do, and it's, yes, go ahead. I see you are puzzled. No, okay, all right. Yes, RPN. I have written RPN, but what do you mean?
You wrote PPN.
Sorry, yes, that's what you mean. Yes, sorry about this. So in the Feynman parametrization, what is this projectivization is also known as the Cheng-Wu theorem. You know that in the Feynman parameter, it's a delta, 1 minus all the Feynman parameters. This you can change into just one of them or any subset of them, or in fact, any linear combination. So this shows the, in reality, projective invariance of the integral, and you can do something similar also here in the Lipomeransky parameterization. That's the gist of it. And now, yes, I'm sorry for this perhaps slightly technical, but I wanted to be concrete on the steps. So now I will hopefully touch base with something that is more familiar to most of you, and was also featured in Andrew's talk. So from this representation now, so we can obtain the following Landau equations. So these are, this is the first of the two equations that Andrew talked about. You have a denominator, so a necessary condition for the integral to have some singularity is that the denominator vanishes. And then you also have the second equation that also featured in Andrew's talk, that this is and this ensures, for example, that the integrand, the contour of integration gets trapped between poles of the integrand. The integrand has poles, and they trap the integration contour so that you cannot analytically continue it, and then it's a genuine singularity of the integral. So these are, how the Landau equations look in this particular representation. And for the experts, you see that since I have x0 here, I can also, one of the solutions is that u equals 0, so this also catches all types of Landau singularities, type 1 and type 2, so not just type 1. The deal is that solving them remains a challenge, solving these equations in any form. And they are nonlinear. And furthermore, there are solutions that scale differently. Let's say that go to 0 at different rates. And there are no systematics how to obtain them, how not to miss all these solutions. So this is, this is why alternative methods have developed that either look at subsets or supersets of the Landau singularities. And instead, in our work, let's see, probably I should erase this. Yes? The Landau equations are necessary conditions, not sufficient.
So you give a superset.
Yes, you could have cancellations from numerators and so on, indeed. But let's say there are even, more spurious candidates that are not really even solutions, let's say, of these equations, so to speak. And so instead, as I mentioned, well, no, I didn't mention. So instead of these equations, we will rely on a different, more robust definition of Landau singularities, which is due to Pham. And this also goes by the name as his Landau variety. And there have also been, this is work of the 70s and 80s, but it's definitely been, and it was quite mathematical and hard to digest, but more recently it has been re-examined, and for example, Andrew and friends have also at least been inspired or, applied some of this machinery, at least for generic Feynman integrals with different masses and so on. And in the end, at least our view of this way of understanding Landau singularities, and this I will try to summarize in most simple terms, yes, what one is really doing with this language, with this machinery. It boils down to considering the integrand really, so GH equals 0 as a variety. It is a polynomial equation with respect to the integration variables. So it depends on both integration variables and external kinematics. And then what you do is you detect values of the external kinematics, of external kinematic parameters for which this changes topology. So let me somehow, oops, that's not what I want to do. So, but yes. This is, in our understanding, the most efficient and productive way to look at Landau singularities. You have your integrand. It's a variety. It depends on the integration variables. It also depends on the external kinematics. It has some topology. As you vary the external parameters, the masses and momenta, the topology also changes. And the Landau singularities are when these topology changes occur. And so I will visualize this also in a simple example, which will hopefully make this word more transparent to everyone. So let's put this into pictures. And let's assume that we have that our G equals, let me color code again so that we are keeping track of everything. Okay, so let's say x2 minus 1 squared minus x1 minus z, and then x1 squared. Okay, so this is, so let's suppose that this is an integrand, okay, the denominator of an integrand, and these are the integration variables, and this is the external or kinematic parameter. All right, let's now plot this curve, okay, g of h equals 0. So this is a toy example. So this is not an actual integral. I'm just, yes, you could say x0, x1. Sorry. Yes, you could say x0, x1. That's not a problem. Yes, but this is why this is a toy example. This is not, I'd say, this is a toy example. This is not an integrand of a Feynman integral. This is just, yes. Yes, this is not defined in projective space. This is just an illustrative example. Yes. Yes, I use the same notation. In fact, in the paper, we use f. Just some integrand, okay? Some denominator integrand. So this is why I say to example. This is not really a Feynman integral. So you could name it differently, but let me try to plot. All right. So let's say that. Sorry. Yes. So let's say that z equals -1 greater than 0. Z equals 0. Z equals a half greater than 0. Okay. And now let me try to plot this curve. So in this case, it looks like this. In this case, it looks like this. In this case, it even breaks up into two components. So what do we see here? We have, let's suppose that we started with z negative, okay? We get a curve that has one closed loop, okay? Clearly also here it's singular. There is no way to define the tangent place to this point. As you increase z, you go to a point where this loop degenerates. Clearly, it changes topology.
Sorry, what is z again in terms of x1?
Z is an external parameter, a parameter of the integral. In our case, a mass or a momentum. What's that?
It's not here in the GH.
This is Z.
Oh, z. Okay, sorry.
And so this is, and okay, if you increase, again, another change in topology. From one component, you get two components. Here it's smooth, but you get two instead of one connected components. So this here is the topology change. And therefore, the Landau singularity. If you were to consider this integral, it's not a Feynman integral, I agree, but just, yes, you could also call it G, consider it, you could even consider it without the exponents, just this object alone. You would, by other means, find that when you take z equals 0, this becomes singular. So in this example, it's hopefully at least illustrated why changes in topology are important and why we should care about them.
So for this example, you always restrict this x1 to be real, to the complex bed.
So let's see. Yes, indeed, in this example, we have restricted the x's to be real. That's true. Sorry? Yes. Real topology. You are right. Sorry? What is the region of integration? You could take from 0 to infinity. You could take from 0 to 1. You would still find, yes, this singularity for the integral.
What about some derivative points? x1 plus 0, x2 plus 1, this product comes to x to 0, right?
When you take both, you say x1 to 0, x2 to 1. Yes. Yes, very good. Thank you, Einan.
So it doesn't matter that there are some problems with this.
These problems are those issues, if I'm not mistaken, were independent of the value of C, which is kind of like the singularities problem.
Exactly, exactly. Yes.
You could do this in dimensional regularization and there be some holes in understanding.
Precisely. So you separate indeed IR and UV from kinematic singularities. More questions? Well, you can take the equations. You can take the equations and solve them, and you will see that indeed what you were pointing out, that x1 equals 0, x2 equals 1, solves these equations provided z equals 0. So in this example, it's an easy solution of these equations. It's just to illustrate the power of topology, of thinking about changes of topology. Of course, you can do it, no problem, with the equations I presented. Yes? So it does, it holomorphic. So it doesn't, you mean, so these are real, this is the real projective space. This is a very interesting question. I hadn't thought about it, but yeah, thinking of, I don't know, BCFW and Park Taylor and holomorphic. But it's, maybe we can continue, yes, discussing after the talk. And in the end, you are looking, yes, for even complex solutions of the Landau equations. You're not restricting to real or positive. You're looking for all complex solutions anyways. But the point is that, let me see where I write it down. I write it down here. The point is that exactly such changes in topology are precisely, are precisely what is algorithmically captured. So by Whitney stratifications. And this is how they come into the play, into the game of analyzing Landau singularities. And without further ado, I can try to introduce these Whitney stratifications. So, and this will go into at least 3 steps. So let's start with Whitney stratification. of a variety. And I will, well, first, I should say what a stratification is, all right? So before I go into the Whitney. So a stratification is, okay, for physicist standards, a decomposition, okay, let's also call the variety X, okay, is a decomposition of X into subvarieties. So let's also, to be concrete, of dimension D. It has dimension D. And so if you stratify it, you split it up in a way such that the open so-called strata and these are the so the points in Xi that are not contained in Xi minus 1, these are smooth manifolds. So smooth, yes, are smooth. So this is what a stratification is. Again, take a singular variety and break it up into pieces that are themselves smooth. In this case, if you, let's say, remove this point and make it a separate stratum, you have possibly an open, yes, manifold, but everything else is okay. So you have no problems with, yes, singularities of varieties. So this is what the stratification is. And then what is the Whitney part? The Whitney part means that also so-called Whitney's B condition holds for all pairs. Yes, because you cannot define a tangent space, yes, on this point. And it is related exactly to some Jacobian, yes, of the variety, yes, vanishing, yes. So higher derivatives, you can think of higher derivative vanishing, yes. Mm-hmm. Maybe we can hold on to this thought, take note of it, and continue at the end informally and so on, just so that we manage to, yes, present some of the main ideas. So now we'll go and give a definition that is rigorous, but okay, slightly impermeable, but then I will visualize it and see it in an example. So bear with me for a moment. This will be the most, so to speak, technical part, and not so much actually. So let M and N be strata, and These we said are not necessarily closed, so let's consider their closures. And let's say that the closure of M is contained in the closure of N. So, okay, you can, if you remove this point, then you can consider the closure of, yes, the part on the left and so on. Then Whitney's B condition at point X inside M, so the smallest of the two strata, with respect to N, so it is discussed pairwise, is satisfied if for every sequence of points, let's say PL inside M and QL inside N, both limiting to X, to this point X, the limit of, let me again color code, of the secant line between PL and QL is contained in tangent plane, in the tangent plane, in tangent plane to N at QL, in the limit where QL reaches X. And so I said it in words, let's visualize it. Should I guess here is the best place. All right, so the example, this will be a 3D example. It's a so-called Whitney cusp. And it is the variety X defined by the vanishing of the polynomial X squared plus Z cubed minus Y squared Z squared, which, as I mentioned, is in three-dimensional space. And this notation, just a word of notation, V of G1 dot 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 GR is really all values of X in some field, such that all these equations are 0. Simultaneously. So this is just one equation. We could have also more equations simultaneously following. And now we'll try to draw this, and let's see how it goes. So this should be the y-axis. And then on the xz plane, this should look like this. Also, let's do it here. All right. So there is this bit of the surface, and then this bit of the surface, and then this thing shrinks. Let's see. So this loop shrinks. Let's try to put it also somewhere in the middle. All right, so if I start here, and I go from the back side, and I return, I go here, same in this way. Let's say I go here, go from the back side. Yes. So this loop shrinks and shrinks until it contracts completely at this point. And so this is my origin. And let's put, what colors do I have? So,
you also change the orientation of the loop, right? There's a twist in the middle.
you mean here and here, the way I did it?
From left to right, you change the orientation, right, of the cuts.
I'm not sure I follow what you mean.
So like first you go from like behind to front, and then like once you move right, then you go from front to behind. Or?
You mean the way I've drawn these, or?
Like the way how this folds. Does it like, is there like a twist or a change in the middle, or like you just like shrink it?
You just shrink it. Okay. You just shrink it, and I should include this as well. So you just shrink it. Yes, exactly. So this is the z-axis, and this is the y-axis, the x-axis. Sorry, the x-axis. So let me write down what the Whitney stratification is, and then we can, so. This is, okay, X itself, the biggest stratum, and then you have essentially the y-axis, and then you have the origin. So and let's look at this and make a few comments. The first thing is that, okay, from our previous discussion, it's clear that the y-axis, on the y-axis, this variety is singular. There is no uniquely defined tangent space in it. So you could just break it up by removing the y-axis into a separate stratum. This would give you, this stratum, and then some other open components on top and below. And this would desingularize it already. That would be a stratification. But it is not, this is not Whitney, because here we also separate this point further. We take this as another stratum. So we split this y-axis into a positive and a negative half-axis, and also this point. And notice that this particular Whitney stratification, which I will show how this definition applies to it, does capture changes in the local geometry along this axis, or topology if you wish. If you are on this axis, then you see a loop on the transverse directions to y when you are in a generic point, but you see no loop here. So already by looking at this, you smell that this Whitney stratification does correctly capture changes in local geometry or topology. And now, are there any questions? Or maybe I should, let me also illustrate how this definition works in this example. So we can, I guess blue I haven't used. Let me use, or no, let me use. So let's say that we have some sequence here. This is our P1, P2, and we want to reach here. And this is our Q1, Q2, as we approach here. So clearly, the secant line, is on the z-axis, also when you reach at the limit point, whereas the tangent plane is actually, sticking out of the surface. So let me make the tangent plane to this. So this is component N, I should say. This is component N. This is component M. And so when you arrive at this point, you have the tangent plane. So let me draw it. So this is the tangent plane on this point. So this is how this geometric condition, Whitney's condition, the fact that at this point you don't have that the secant line lies on the tangent plane, means that it violates Whitney's big condition, and then you need to further stratify to make a more a finer stratification by taking this point out that capture changes in local geometry or topology, which is one of the main ideas behind this story. So let me pause and ask if there are questions, and I understand that this was a bit technical.
So I don't quite see it, why you need to remove the point 0, 0, 0 from the y-axis. I mean, like the y-axis itself, does it also satisfy these conditions? I mean, it's smooth and like it's, I think it also satisfies the second condition. Or like, what's the problem? Why do you need to remove the point 0, 0, 0?
This is what I was just saying, that consider this sequence that goes along this top side on this manifold, and also along the y-axis. And so this is a sequence, these points approach the origin. The secant line itself is parallel to the z-axis, whereas the tangent plane is sticking out of the, so therefore, at this point, this condition does not hold.
But like at no point does it hold, right? There's no point where it holds.
No, if you apply it on some other point here, you will have to take different limiting sequences. But in this case, yes, you can show that it does work, yes. Mm-hmm. More questions? So we've seen what a Whitney stratification, yes, go ahead. Very good question. Very good question. The reason why Whitney stratifications got mathematicians, algebraic geometries interested is, first of all, it was shown, existence was proven that every algebraic geometry admits a Whitney stratification. And later in the 80s, early 80s, it was proven that there is also a unique minimal or coarsest Whitney stratification. So let's say a smooth piece, you can break it up as many times as you like, and this holds. But there is a unique coarsest or minimal stratification. Very good question. Okay, so with this, I will then use one more board with, yes, let's say it's brief description of definitions, and then move on to examples and close. And I understand that, yeah, afternoon is not the best time for technical details and heavy talks. So I talked about the variety, but in fact what we need is a Whitney stratification of a map, of an algebraic map F from X to Y. So this is yet a layer of structure. These are themselves varieties, as the ones we just dealt with. And I will skip now the details, but it is at least in the first instance defined as a pair of stratifications of varieties. Okay, so X, let's call it dot, Y, let's call it dot, where this is Whitney stratification of X and of Y. So for this, we apply just what we learned, what I just presented, with one additional condition on this map. And this condition has to do with the differential being submersive for the technical experts, and it has to do with also the original way of FAM of formulating in his language the critical values of the projection map. Anyways, but this is encoded in this additional condition that I will not present, but you are welcome to ask questions. And let me also put it on words. There exists a unique minimal Whitney stratification of a variety and of a map. And for the variety, this is the word by Teissier in 81. And for the map, it follows very easily among the same lines. And with this, I can now give the definition of the Landau variety in this language. So reformulate FAM in a practical manner. And let me erase here. Good. So, the Landau variety. We consider Feynman integral in this homogenized Lipomeransky, in homogenized Lipomeransky. That's why I had to introduce it a bit early on, even though it wasn't very easy. And then we let our variety be given by the vanishing of not just the integrand, but also all coordinate hyperplanes. And this is a variety, we think of it as in both the space of integration variables, n of them as the number of edges, and external kinematics. So these are integration, and these are kinematic variables. So this lives inside this space. It depends on both x and momenta, and we use both. And then we consider also the projection map from this space, from the variety to just the space of external kinematics. So this is a projection. Yes, you care only about the space of external kinematics, kinematic variables. Then,
Where are the commas in your variety? Like, is it the product x0, x1?
sorry, dot.
All the product of everything.
Yes.
Also with the polynomial.
Yes. And then the Landau variety, capturing all singularities. Is the variety y n minus 1, sorry, m minus 1, appearing in the minimal Whitney stratification of pi. Yes? You have the? Yes? Without necessarily, so you're saying you would expect this to vanish and these to vanish for a singularity. This is a product. This is a product. What can I say about this? Well, first of all, I'm glad that you agree that, okay, we need to include these because exactly we do need to care about endpoint singularities. So we definitely need to include these. Then the question is why you consider the product and not just simultaneously these to vanish. What I can say is that we are not interested per se in the singularities of the variety, but on the of the projection. So Yes.
Two steps. The first step is to identify the singularity, second to project. But what is not clear from this is how condition, hinge condition, relative condition is taken into account.
I think that's the y sub n minus 1, right? That's the mechanics case we were looking at, where you have the derivative that's right?
This is yes, this is a codimension 1, yes, space. So it's uh, so yes, what I can say right now is that for sure one needs to take account also of endpoint singularities, and that essentially this is a rephrasing of of FAM's definition in terms of the, yes, the critical values of the projection map. So this is really a rephrasing of FAM's definition in the Lipomeranski representation. So one would have to go like deeper into translating between FAM's language and the Landau equations, which is not always the simplest thing to do. That's what I can offer right now as a partial answer, but I'm happy to think about it more and discuss it after the end of the talk. I should say also the work of, I was planning to mention them later on, but the work of Berghoff and Panzer. So yes. So Berghoff and Panzer. They have a similar construction in the in Feynman parameters, and we have checked that essentially they are equivalent. The issue for them is that they have a definition, but they cannot construct, let's say, the Whitney stratification. The definitions are equivalent, but there is no constructive. Okay, I guess, yeah. I forgot to mention, or I was planning to mention it afterwards. The advantage of this is that there are algorithms for computing this Whitney stratification of any map, of any algebraic map. And so for this, there are exactly algorithms. By our collaborator and also Nanda. So that's the virtue or the merit of yes, reformulating FAM's work in this way, that you ask your neighbor who happens to have completely, like, already worked on this example, on this, yes, objects and this language already, and you can immediately use the program that he has already written. But let's come back to this after the end of the talk. I guess I only have 5 minutes. We had several questions already. I can erase this and just very briefly flash the examples that we looked at and the conclusions and conclude. Okay. So, computed examples. And, okay, this will not impress anyone. This is a generic bubble. This might get people more convinced. Oops. So this is the 2 mass hard last box, P1, P2, P3, P4. And then finally, we looked at the parachute. P3, okay, P1, P2, M3, M4, M1, M2. Okay, and so the importance of this example was that you could, okay, you have your space of external kinematics spanned by M1, M2, and P square, and then Y2 is the Landau variety of the diagram, and then Y1 contains the Landau variety or the Landau singularities of, let's say, the M1 goes to 0 limit. So you can also, for free, in other strata, get the Landau singularities of all graphs obtained by the original one by, for example, setting masses or momenta to 0. So this was the utility of this example, and if there are questions, I can mention it further. Here we found 9 components, including a letter, if you wish. In this case, the variety, sorry, the letter and the Landau singularity coincide. There is P square minus S minus T, where this is S, and this is T, and this is missed by PLD. And finally here, so this is a 7-dimensional space. So you can see to the 7, you have 3 momenta square and 4 masses. This is, for the time being, infeasible computationally, but we computed a particular restriction where you set, I don't know, M2 square equals M3 square equals P2 square equals 0, and then some other non-zero values equals minus P1 square equals M4 square over 2 equals 1. So this is just, in the end, depends on M1. On just one P. I guess, in P3. It depends on P3. But again, we again found the singularity that was again missed by PLD. In fact, in this case, PLD missed more than one singularity. It missed 2, and we compared to the work of Berghoff and Panzer, who indeed computed all singularities in the generic case, and the one that we found in PLD was missing was a limit of it from general kinematics to this configuration. We also did this actually analytically. We also computed the integral analytically, and yes. So singularity. We found the singularity P3 squared minus 1. This is the one that is missed, let's say, by PLD. Again, go ahead. This is an excellent question because it relates to my outlook. So, okay, just to summarize and get to this, I hope I convinced you that the approach of Whitney applying, reformulating the calculation of Landau singularities in terms of Whitney stratifications gives you a robust way to get their complete and non-redundant set. That there are already packages in the market that one could use. That as a bonus, you get also Landau singularities of limiting graphs. As far as the future is concerned, we would of course love to make it more efficient by taking advantage of the special structure of Feynman integrals. What we discussed is not just for Feynman integrals, it's for any integral, be it also related to gravitational waves or any integral really. It would be very interesting to see what happens to the integration variable. This is important in both, expansion by regions and numerical integration. And our feeling is that it must somehow reside in the Whitney stratification of X, not of Y. It must be, this information must be contained in there. And yes, maybe we could also prove some remarkable cluster algebraic structures that of symbol alphabets related to Landau singularities obey, or even extend the scope so that we directly get symbol alphabets and not just Landau singularities. Thank you very much for your attention, and I'm sorry if I went a bit too technical at points.
Very important to have a complete set. This is extremely important task for many applications, as you said. The other thing I wanted to say is that having the singularities of the limits is very important as well. And there is a very curious equation that somehow taking the limit was not commute to identify the singularity. Basically, the singularities of a limit are not at all related to the limit variety that we found before. So this is an extra advantage. This is a very important advantage for dimension. For expansion by regions, in particular, one needs to know the singularity in the limit around which you expand.
Thanks for your comment, Einan. And indeed, this is a feature, and also it has some drawbacks, because if someone is not interested in it, it requires more time to also compute these components. We talked about this component, yn minus 1. In the end, the algorithms compute everything, and you cannot just stick out. You cannot just separate out this component. So you do get this at the very end. You get all the information. And it's good that this is needed. It's even better if one could perhaps specify if this information is needed or not, and have alternative routes where one only cares about the original graph and gets the answer in a faster way, or gets the full thing more efficiently. Thank you very much.